Hi everyone, welcome to my talk, Let Pods Sort Them Out, about anti-disaster pod scheduling. I'm so happy to have you here with me. So before we get started, a quick few words about me. I like to go by the moniker Gil of all trades. I'm a DevOps team lead at Kim of Finance. I have a blog, this is its URL. I'm the founder and admin of the Israeli Women in DevOps group. I'm a volunteer, activist, blogger, and, well, speaker. Okay, so what do we have planned for today? First, we're going to have a brief recap of Kubernetes scheduling and disaster recovery planning. We're going to put some context and scope our discussion about scheduling and disasters. Then we're going to talk about the primitives of an anti-disaster plan as offered by Kubernetes. And then we're going to look into some anti-disaster scenarios and see how those primitives that we have surveyed earlier may apply. And then we're going to wrap it up. Right. Okay, so a brief recap. I'm sure that you're all knowledgeable in Kubernetes, but let's just remind us all that Kubernetes, by its nature, is an orchestrator. Its primary task is automating software deployment and scheduling. So allocating the right virtual place for a workload is one of the primary tasks by Kubernetes. So it's no wonder that it has so many flexible and tunable options with regards, given that it's so endemic to what Kubernetes does. As for disasters, well, disasters comes in all flavors and shapes, but since we're talking about scheduling and Kubernetes, so one of the things that Kubernetes does is responding to capacity loss, irregardless of the source of the capacity loss. So when we scope disasters for the purposes of this talk, we're talking about something that caused us to lose our capacity and how we restore our service with regards. Okay, great. So let's look into some building blocks. So first, scheduler is a concept that allocates resources from availability pools, considering a set of constraints. And it's important to remember that reliability or resilience is not the only thing that you can optimize for with regard to scheduling. One may optimize for efficiency, for cost. So thus, it's our duty to configure Kubernetes to provide us with the resiliency and reliability that we require in handling disasters. Okay. Now, as we have mentioned before, that Kubernetes scheduling is so very endemic to what the product does, so it's no wonder that it was made pluggable. So we have a default scheduler. It's wonderful. It's useful for also many things. It has many configuration options, but other schedulers may exist or be written to need if we find the need to do so. So one prominent example is EKS Fargate. EKS Fargate is the serverless offering coupled with Elastic Kubernetes service, and it's powered by a custom scheduler. When the custom scheduler detects that a pod should be run on Fargate, then it allocates the Fargate resources and makes sure that the pod is placed on those resources and not handled by the different scheduling policies. Okay, great. So let's see what Kubernetes does with scheduling. So first is matching pods to nodes. We have node selector, we have affinity and anti-affinity, which tell pods that they want to be on this node or that they don't want to be on this node. Now, as we can label things dynamically, we can also enable dynamic policies. Let's say that, well, some of them even Kubernetes applies internally, like nodes that are stressed will have a label that they are stressed and the pods will not get allocated to them. This brings us to the next slide. We have manual labels that we have placed for our own routing purposes. We have implicit labels, like the operating system. And if we're running in a cloud provider, then we may also have cloud provider labels, such as availability zone, or let's say instance type, or instance purchase option, and so forth. Those are really flexible. So one thing that matching pods to nodes with affinity, anti-affinity node selection that we cannot do without a specific declaration is something called topology spread. Let's say that we have some availability zones or some values. What we want to say in a topology spread says spread the pods from this deployment or whatever across the different values that this variable can hold. This is a very handy thing, so we'll check it back later. I think it kind of, well, it's pretty obvious what we're going to use it for, but it has a hidden use that's not so obvious, and definitely do remember that one. It will come back. Okay, we have specified, we know how to specify how pods get allocated to nodes, and then we have the opposite. Taints repel pods that do not tolerate those taints. This is used to, let's say, save unique or otherwise special nodes from holding, let's say, less important pods. Let's say that you have a GPU node and you want to make sure that it's used only to run GPU workloads, even if theoretically it can run non-GPU workloads, that would be a waste. So you use taints and tolerations to make sure that other pods don't get scheduled on these GPU nodes. It can work on other important pools just as well. Let's say I want to dedicate the node pool to something else which is important. Yeah, we're definitely going to see that come back too. Okay. And then we have tuning. Like I said, the default scheduler can be tuned for so many things. There's so many options. I want to just discuss one, for example. Let's say that you have many, many nodes in your cluster. If the scheduler were to find the perfect node, it would be very costly in terms of compute and in terms of scheduling time. So you can tell the scheduler, no, you don't need to look at all possible candidates. You can take just half of them, just a quarter of them, and so forth. And that saves a lot. You will lose some accuracy, but obviously will gain on performance. And if you have lots of nodes, maybe you'll still get good enough scheduling this way. And this is just one example. I'm not going to go over all of them, obviously, because there's just so many of them. Okay, great. And then we have something called priority classes. I like to call this a hidden gem. I haven't seen nearly enough use of that feature. Priority class basically tells Kubernetes that some pods are less important, so to speak, than others. And if it needs to schedule a pod, then it can deschedule a pod with a lower priority class in favor of one with a higher priority class. So obviously, we're definitely going to use this one. And then we have pod disruption budget, which to my humble opinion, it complements priority classes. Pod disruption budget tells Kubernetes, hey, try not to disrupt this too much. I need at least one pod of these, and so forth. Okay, so we've talked about how Kubernetes allocates resources for pods, but ultimately, you will reach a situation where more resources are needed. And then we scale the cluster rather than allocate resources from what we have right now. A cluster autoscaling is actually a component which is external to Kubernetes. It comes with a distro. It's developed by the CNCF as well, but it's spun off to another project just because there's so many cloud providers, and obviously you might not be running Kubernetes on a cloud provider, so cluster autoscaling might not even be relevant for you. Thus, it's been spun to another component called cluster autoscaler. It's the common workers. It's been used very successfully in many deployments, although one size may not fit all. A few years ago, AWS decided that they wanted another node scaler, and they started developing the Carpenter project, which has recently gotten support for Azure as well. And it's not the only one. There are further third-party solutions as well, all focusing on different things that they want to achieve. Wonderful. I think we've covered just enough to start looking into disaster scenarios and how we mitigate them. So the important thing to discuss about disasters, in my humble opinion, is that if disaster strikes, you have not much more to do but just use the playbooks that you have planned in advance. But disaster recovery is 95% pre-planning, at least. Okay, so we're going to look into three disaster types. One is the loss of a single very, very important pod. The other is a topology failure. We have a failure in which a certain availability zone has failed us. And last but not least, we're going to look at a totally random failure. So if you have a single important pod that our cluster cannot or will work significantly less efficiently without. So one of the nice things that you have in Kubernetes is something called leader election, which we haven't discussed, but basically every single pod can be turned into, let's say, an active passive multi-pod deployment, because one will the pods will elect the leader amongst themselves, and once that important pod is lost, its secondary will see that it needs to be elected as a leader and start to kick in. This is complemented by priority classes and pod disruption budgets. Obviously, if this pod is important and we assign a high priority class, it will boot a less important pod. Now, sure, it may boot something else which is important, but not as important as this particular pod. And complemented by pod disruption, but it says, hey, okay, you want to do things? Okay, that's nice, but please try not to disrupt those pods. But if you have something which is so important, then assigning a designated node group, which is tainted such that it can only run this pod, or let's say a set of important pods, or you can use Fargate for that to a very similar effect, and then you are less hurt by other things trying to deschedule it or loss of capacity and so forth, because you're using a designated node group with its own capacity. And last but not least is over-provisioning. Over-provisioning is actually going to return in all those scenarios, because if you have more capacity and you lost some, then you have some cushioning. But the big drawback of over-provisioning is that obviously you have to pay for it. So we're trying to do as much as we can without over-provisioning. And then we have a group of pods facing a zone of a topology failure. It could be an availability zone, it could be a rack, and so forth. So let's look into that one. So first thing, priority classes will allow us to make sure that important pods recover faster. And if we can, if we assign high priority to certain pods that are, let's say, the single one of those services, then you will at least get one of those services as a higher priority, which is very nice. We can say, okay, this service is available at least and doesn't have like 0 replicas. And then we have a topology spread. Obviously, we would like to spread our resources such that in advance, such that losing a zone or a rack would impact us less, because we've spread our workload across some of these. So if, let's say, we have 3 availability zones and we lose 1, then obviously we lost up to 1/3 of our capacity and not much more. Over provisioning, as stated. And here's another thing to consider. When we lose capacity, autoscaler will kick in and try to bring it back. We need to tune it in advance, if possible, for balance, for availability zone balancing, but sometimes it may not detect that a certain zone is having trouble and try to allocate more resources from it, which will obviously fail, or maybe even fail byzantinely. So we may want to adaptively reconfigure the autoscaler and tell it to ignore this particular zone, at least for the while, until we can say that it's reliable again. And here's a nice bonus for spot failures, which is also something which is a bit similar. We can use topology spread here as well. If we spread our pods across on-demand and spots, then it is guaranteed that the spot failure would hurt us only as much as we allow the spread to do. So I'd say maybe 50-50, or maybe if we have tunable spread, then maybe even less, which is very nice. Last but not least, we have a generic failure with no pattern. As we have no pattern, it's a bit hard to, let's say, plan for it in advance. So again, priority classes will hasten the recovery of important pods over less important ones, and will allow them to boot them, and like reducing the blast radius. We have over provisioning, as discussed, and even better, if we have a failover site for these kind of scenarios, then we might want to issue a full failover. Again, costly, but obviously needed for quite a few use cases. And last but not least, we have autoscaler tuning, as discussed, but also third-party autoscalers, whose functionality is dedicated to bringing capacity back as soon as possible over things such as cost or efficiency, things like warm pools and so forth that are offered by certain third parties. Wonderful. Okay, so let's wrap it up then. We discussed capacity loss disasters. We discussed our toolbox that allows us to plan ahead as to how to respond to those kind of failures, and then we analyzed the failure scenarios from the simple to the hardest. And here are key takeaways. 1, plan ahead, because disaster handling is 95% before disaster even strikes. Second is know your toolset. Your toolset can be open source, it can be provided by your cloud vendor or even other third parties. And last but not least, have a playbook, a well-defined playbook that says, okay, if something like this happens, this is how I want to respond, and hopefully with some clicks or CLI commands, you can execute that playbook and respond to the event swiftly and accurately. Thank you so much. Feel free to hit me up on Twitter. My Twitter handle is Gil Bahat, and there you have my mail. Thank you so much for having me.